Yeah, can you all hear me now?
Yes, ma'am.
Yeah. So is this okay? So therefore, we can say that the assumed stress function.
Ma'am, we
I
can't
don't
see
Ma'am,
the
it's not presenting.
Ma'am, I don't know, you're again muted.
Is this? Am I audible?
Yes, ma'am.
Yes, ma'am.
Yeah. So you can see the whiteboard, I guess. So
No,
No,
ma'am.
we
We
can't.
can't
No,
see the
ma'am.
board.
is it visible now?
Yes, ma'am.
Yes, ma'am.
Yeah. So so as I was saying that therefore, since the stress function phi is satisfying both the criteria, therefore this is an acceptable stress function. Okay. So any questions here? Is this clear?
Yes, ma'am.
Yeah. So to answer one of your question that whether we can do it for all the cross section. Now see, this is an ad hoc method that we are doing. So there is no formal method of finding out a stress function. Okay. So finding out a stress function is always always left to the engineer who is solving the problem. So it may happen that for various cross section, you can adopt this and you can get a acceptable stress function. But there are some cases, like say a rectangle or so, where you cannot adopt this method and get an acceptable stress function. So there you might need to adopt some other method to find out the stress function. Now my point is that, so what you have to do is that you have to somehow, by some means, find out or assume a stress function and see whether it is satisfying the two criteria. Okay, the method that I am describing, the method of finding out the stress function that I am describing now works for many cross sections. But saying that, I should say that it's not a universal method. There could be a cross section where this method will not work. Okay, so your job is to somehow get hold of a stress function, and then you can say it is satisfying the criteria for Prandtl stress function only when it is satisfying these two criteria. So if you, by any means, if you can find out a stress function which is satisfying the two criteria, then it's your Prandtl stress function. Okay, then you can go ahead and it will give you all the correct answers about the stresses, about the warping function and all. Okay, so the next job is to find out the torsional rigidity.
Ma'am,
Yes,
ma'am, is the psi function here unique or there can be some other functions as well?
it's unique. You cannot get hold of two phi function which is going to satisfy the criteria.
Okay, ma'am.
Okay, so now I have expressed from the previous theory, from the previous lecture. We know that the applied torque is the area integral of the stress function phi. Now, if I write down the expression for the stress function, I get this integral and I just split it and I get an integral of this form. Now, if we closely look into the integral, we can observe certain things. Let me see. So, can someone tell me what does the first term of the integral denote? Can someone tell me what is the first term of the integral? What does it denote? What does it represent?
Ma'am, is this the area moment? IXX.
IYY.
Okay, IYY.
Yeah. So this is IYY. This is IXX. And this is okay. So we know we can always find out the IXX, IYY and the area of the ellipse. We know how to find it out. Okay. You have done it in your first year mechanics. So I am not going into the details of it. If we solve this equation, then we are going to get mt in terms of okay. So if we evaluate the integral, we will get the moment, the torsional moment of this form, which is g theta pi a cube b cube by a square plus b square. Therefore, the torsional okay. So this is going to be the torsional rigidity of the elliptical shaft. Fine. Any questions here? Is there a question? Okay. So let me move into the second part. So next is to find out the warping function.
Ma'am,
Yes.
ma'am, in the previous part, we could have directly calculated the polar moment of inertia for the given shape, and then we could have directly done like my gj theta equals mt. Will that be right?
The polar moment of inertia will not give you the torsional rigidity for all the cross section.
Uh,
I will
for this,
confirm this once more. That's what I think. I will confirm this. I have a doubt in this. I will confirm it again. But I think the polar moment of inertia is not always the, because see, the polar moment of inertia often is ixx plus iyy plus you have a also here and area also here. So anyhow, let's not discuss. I will check it once and confirm.
okay, ma'am.
Okay. Okay, so our next job is to find out the warping function. So someone tell me how to find out the warping function? What are the steps from the Prandtl stress equation? How can we get the warping function? Any idea? This so the deformation u and v is always going to be of this form, and you can very well assume this. Okay, you can always say that u is going to be minus theta into yz and v is going to be theta into xz. So what is unknown to us is the warping function psi. Now my question is that how do we find out psi from the stress function phi? Any idea? Anyone? So the clue is the shear stresses. What are the shear stresses, and can you relate the shear stress to the warping function? Anyone? Okay. So
Ma'am,
let me, yeah. Yes.
Ma'am,
using dou u by dou y plus dou v by dou x,
Yes.
that is the shear, and I mean, and shear function equals to.
Yeah, yeah. So we can obtain the shear stresses tau xz and tau yz in terms of our stress function. And we also can obtain tau xz and tau yz from the displacement function. Now, if we relate these two, we are going to get the expression for the warping function. So let us do it. Okay. Let us try to solve that problem. So tau xz Okay, so this is one expression for del psi by del x that is coming from the first expression. Okay, from we can get a similar expression for del psi by del y from the next equation. So let us try to find that out. So we have to just remember this, and let us try to find out from the next equation.
ma'am, isn't it del p by del y?
No, tau yz.
Oh, okay, okay, got it, got it.
So Am I doing it correctly? Let me know if things going wrong. So 2b square minus a square minus b square. Yeah, sounds good. Okay. So I this is equation 2 and equation 1 was okay. So I get two partial derivative equation for psi. One is del psi by del x is this function, and del psi by del y is the similar function but with x. Now let me try to solve this. So if I solve this, I get psi equal to plus a function of x, right? Because it is a partial derivative, it is not going to be a constant. It's going to be a function of x. Okay. Similarly, from this, I'm going to get psi right? So if I equate this, then is this clear? So I get an expression for psi from the first equation. I get an expression for the same psi from the same equation. And if I have to equate, I of course have to equate them. And if I equate them, I get the two integration constant f1x and f2y, and they are equal to each other. So they have to be a constant. But now if we assume that the shaft is constrained at a point 0 at the origin, then this constant has to be equal to 0. Right? If that is the case, then I can write psi, which is a function of x and y, is equal to b square minus a square into xy.
Ma'am,
Yeah.
ma'am, why is the constant 0?
So we are going to assume that the shaft is fixed at the origin.
Okay. Okay.
Okay. Only then if the constant is 0, otherwise the constant is not equal to 0. Okay. So therefore, this is the warping function.
Ma'am, what do you mean by constraint? Because even if we assume we take a point origin, then we get d by dx equals to 0. So then also we can say that the constant has to be 0.
No, I didn't get your question. Can you tell me once more?
Ma'am, what do you mean by constraint at the origin?
No, I'm not saying constant at the origin. I'm saying this too is a constant. Okay, now I'm saying if I consider the warping function at x and y equals to 0, that has to be equal to 0. So therefore the constant is 0.
Yes, ma'am.
Okay. So is there any other question? Anyone else has a question? So in summary, so So in summary, what we have understood is that, so if we need to find out the torsional rigidity and the warping function, we have to start with the stress function, use the expression of the moment, torsional moment, with respect to the stress function, and therefore we can get the torsional rigidity, and we can also get the shear stress distributions. From the shear stress distribution coming from the compatibility condition as well as from the stress function consideration, we can equate and find out the warping function. Okay, so that brings us to the end of this question. So I will move into the next question. So if there are no more questions regarding this problem, is there a question? No, right? Okay. So before I move into the question, let me just say some more non-linear torsion problem. So the thing is that, see, as Pranav Teja has told me, I will be, I'll try to pre-record the lectures and upload it for the theory lectures, whereas the tutorials, I will of course prefer to do it live. Now the issue is that I'm not yet getting hold of a app to do a proper recording in iPad. There are several for Windows and Android, but not many good apps for recording in iPad. So I have tried almost all the apps available. So what I'm trying to do it in a browser-based fashion. Let me see how it works, because with all the apps, the noise level is very high, either or something else. So it might take some time before I could figure out a proper recording methodology. Okay, so the issue is that I'm using an iPad, and it's I mean, my community doesn't use, many of the professors don't use iPad, so I'm not also getting a good suggestion about what app I can use. But it looks like it cannot be an app based, it has to be about browser based. Maybe I can set up a false meeting and record or something like that. Anyhow, I'm working on it, and probably next lecture, which is again very important. The next lecture is going to be on membrane analogy. So there is a lot of things to be understood there. So I will try to pre-record it before Wednesday. Okay. So with that, let me move on to the next problem.
Ma'am, have you tried screen recording?
Pardon?
Screen recording.
I am already doing screen recording live, but is it an app or it's a browser-based thing?
Ma'am, it's like a pre-existing thing. Like I don't know about iPads, but in laptops and all, like there is an existing shortcut in the laptop.
Laptop has several. There are OBS studios which are all window-based. So window-based softwares are very well developed. I mean, OBS studio is there, which is very good. But iPad, iOS doesn't have much of recording app. OBS studio and screen recorder probably doesn't work on an iOS. So I'm trying to see if any one of you know, if anyone of you have recorded anything in iPad, do let me know. I'm trying to figure out. Let's see. If it was an laptop or an Android-based system, it wouldn't have been a problem. But with iOS, there are lots of issues. So I'm not being able to find a good app. Let me see.
iPad has inbuilt screen recorder.
Do you think so? But I don't know, because
Ma'am, it will record your audio.
Yes, ma'am.
Like, it will record your video only, it won't record your audio.
Yeah, that I read. There is some screen recorder. Yeah, but I need both audio and video. So I went through a nice YouTube tutorial on how to record an iPad, but I tried all the apps that they mentioned. There are some glossary, active whiteboard, interactive whiteboard, but none of them is working good. I mean, the noise level is pretty high. So what I'm now trying to do is that set up a false meeting, because these recordings are very nice. I was going through those recorded videos which I've uploaded in YouTube. Those are pretty nice. I mean, so maybe I will set up a false meeting in Team or something and record the I mean, I'll kind of take a false class and then record it. Let me try it that way. That's the last option that I have. Or I will use, so all the faculty, they are using Microsoft Team, or anyone is using Google Classroom, because I'm not very happy with MS Team. So maybe Google Classroom or something may have a better recording app or something. Let me see. It has to be browser based. Otherwise, it's not working. Anyway, let's move to problem 2. Okay, so this problem is taken from Maxon exercise problem. Did I write the spelling of Maxon correctly? I'm not sure, but just maybe the spelling is wrong, but that's okay. So so this is taken from the exercise of Maxon. So I have a shaft with this triangular cross section. Okay, so this is a triangular cross section. The coordinates of the vertices are given. Okay, the xy axis is also given. The stress function is also given. The Prandtl stress function, expression for Prandtl stress function is given. So the question is to show that this stress function satisfies the is an acceptable Prandtl stress function? That is the first part of the question. And the next part of the question is to find out the shear stress distribution and the warping of the cross section. Okay. I mean, the next two part is pretty straightforward. The first part is slightly tricky. To show that this stress function that is given is an acceptable stress function. So what we have to do to prove that this is an acceptable stress function, we have to show that del 2 phi by del x square plus del 2 phi by del y square is equal to minus 2g theta. And we have to show that this is 0 on the boundary. Okay? The problem may sound very straightforward, but it is not so. So can someone tell me what to do? See, the first criteria will be easily satisfied. If you just find out del 2 phi by del x square plus del 2 phi by del y square, you can easily prove that it is going to minus 2g theta. I'm not even doing it. It's pretty straightforward. But the second criteria to show that this stress function is 0 on the boundary is not an easy task. So tell me, how are you going to do that? You can look into the expression of stress function and tell me, how are you going to prove that phi is 0 on the boundary or constant on the boundary, whichever way. So I actually don't intend to solve it in the class. I want to leave it to y'all so that you can think about it and let me know. I'll post the solution in Moodle maybe in 2-3 days. But if you can figure this out, that would be awesome. So I really don't want to solve it in the class. Okay, I will post the solution in Moodle.
In Mexican book, which question is this?
I will give you the question number. You just look into the exercise of the torsion chapter. It's very much there. Okay, I forgot the problem number, but it is there. Okay, in the exercises.
Okay, ma'am.
Okay, so if someone has the answer right now, you can give it to me, or I leave it to y'all and I'll upload the solution in Moodle after 1 or 2 days. Yeah. Pardon?
For the boundary, we can find the equation of the lines. There are three lines.
Okay.
So for each side, we'll find the equation of the line passing through the 2 points and substitute y in terms of x.
Exactly.
For the given
Very
line.
good. What's your name? What can I know your name?
Samik.
Okay, that's an awesome answer. I didn't expect it to come so quickly. Very good. So indeed, that's how you do it. You find out the equation of the line. So you don't even. I mean, the other way to do it, other quicker way to do is just find out the equation of these 3 lines. Take the product of those 3, and that will give you the same equation. Okay. So great. I'm actually very happy. So fine. Anyhow, I will upload the solution. But I had posed another question. I didn't get the answer of this. So I said that you have to tell me for an arbitrary cross section why there is no in-plane deformation. So anyone has thought about the question? So I had posed this question, right? For circular cross section, it is kind of obvious, but for any other arbitrary cross section also, when there is a pure torsion, there is no in-plane deformation. Okay, in-plane distortion. So can someone tell me why is that so? So I have posed this question. If no one has thought about it, please give it a thought and probably answer me. Okay, and so many students have the question regarding the uniqueness of the solution. So there's a good write-up in Timoshenko and Gudia, which is a very interesting read. So I will give you the page number and you can read it. It's actually very nice to read that 1 or 2 pages, which talks a lot about the uniqueness of elasticity solution. So if you want to know further, that is a nice read. So with that, if there is no more question, we will end today's class. So in the next class, I will take up membrane analogy, which is a new theory and which is kind of a very important theory when we are going to slowly move into thin wall structure. So membrane analogy is kind of a basis for thin wall structure. So I will try to pre-record it because this continuous disruption is very, because of internet breakage, is very difficult theory. So I will try to pre. Is there any more question? Anyone has a question? Okay, then thank you. We'll meet on Wednesday. Bye.
Bye, ma'am.